All right, in section 2.2, we talked about invertible matrices and finding invertible matrices, and we came up with a couple of different methods. We had the determinant method that we did. We also used row operations with augmented matrices. We knew that if we were able to find if there's going to be an inverse, that we could row reduce that to where we would get the identity matrix. Remember, the identity matrix is the one with the ones along the diagonal, right? Just to refresh our memory here, I3, for example, would have the ones along the diagonal with zeros elsewhere. So if you have a matrix that's equivalent, row equivalent to that, then you know that you have an invertible matrix. And so we used that property to help us find both whether or not it was invertible and to determine what that inverse would be, right? We augmented our matrix A with the identity matrix. You know, I said I3 here, so it's A is 3 by 3, but ultimately A could be any size with the appropriate identity, any square size. And then after we row reduce that, we get the identity on the left with A inverse. And if we don't, then we know it's not invertible, okay? But this is a pretty arduous process, okay? We had the determinant method, right, for a 2 by 2, where we did 1 over the determinant of A, and we said that we switch the two numbers on the main diagonal, and the two numbers on the off diagonal stay where they are, but both become negative. Okay, so we had that for a 2 by 2, but that right now at least is not terribly generalizable up to higher dimensions. Okay, there is a way we can do some generalizing of that, but for now we just want to say that's our 2 by 2. So it's good for 2 by 2, but we don't have, and this is good for any size, any square size. But we'd also like to use other things we know to not have to go through all these row operations. You know, I have 6 columns across if it's 3 by 3. You know, if it's 4 by 4, I've got 8 columns across. Those row operations are going to be fairly taxing, and so we'd like to avoid that if possible. Okay. And we also talked last time about how the columns are independent because the columns of the identity are independent. So if it row reduces that way, then I know that the original columns of A were independent. Okay, I have a pivot in every row and a pivot in every column. Okay, we also know from linear transformations that a pivot in every row will get us a 1-to-1 transformation. Sorry, let me say that again. Pivot in every row will get us an onto transformation, and a pivot in every column will get us a 1-to-1 transformation. So if I have square, then every row and every column are going to be equivalent, right? If they're not square, then I could have only one or only the other. But for a square matrix, I'm going to have to be bijective, both 1-to-1 and onto, if I get this independence relationship amongst the columns. Okay, so we have all these similar ideas that fit on top of each other, and we like to use them when they are convenient for us. We want to make the right choice to make it easiest on us. Okay, and that's a lot of what the homework deals with in this section. But the big thing here is that we're going to combine all of these things into one theorem, which we are going to call the invertible matrix theorem. Okay, the invertible matrix theorem. Okay, the invertible matrix theorem will also get abbreviated to just IMT. Okay, invertible matrix theorem. Okay, this is also theorem 8. Okay, we will usually call it the invertible matrix theorem and not theorem 8 from chapter 2. Okay, invertible matrix theorem is the name, and if obviously you have a different textbook, it would have a different theorem number and things like that. But in our textbook, it is theorem 8. Okay, now section 2.3 here is a relatively short section actually, but it's an extremely important section because we combine all these ideas we've talked about through chapter 1 up to talking about inverse matrices in section 2.2. Okay, so I'm just going to slide it down here one thing at a time so you can see it. All right, so first let's get the setup, okay? A is a square n by n matrix. N by n and square is kind of redundant, but just to reinforce, these are square matrices. Then it says the following statements are equivalent, which means that for a given A, all of the following statements are either all true or all false, okay? So they're all true or all false. And this is going to have 12 different statements, okay? So these statements are all true or all false, okay, for any given square matrix, okay? So statement 1, it's the invertible matrix theorem. So statement 1 or statement A is an invertible matrix, okay? So we're using that, we're saying these are all equivalent, okay? Most often we're calling it the invertible matrix theorem because we're interested in figuring out if our matrix is invertible. Okay, we have some methods we already figured out, but we're going to codify all these together, and we could say any of the next 11 statements. If I can prove any of these 11, then I know it's invertible. Or perhaps I already know it's invertible, then I get any of these 11 statements with that given quality. Okay, statement 2. A is row equivalent to the n by n identity matrix. A is row equivalent to the n by n identity matrix. Okay, so that's what we use to set up invertibility. That's how we set up our algorithm, right, with the A and the identity matrix augmented together. And we said we could row reduce from one to the other. We could also go in reverse and get us back to our original matrix. If we know that, we know the set of row operations that will yield our inverse as well. Okay, so it's row equivalent to the n by n identity matrix. Okay, statement C, A has n pivot positions. So if you're able, so maybe it's not easy to go all the way to the identity matrix, right? Maybe there's a bunch of hurdles to clear, you got decimals involved or something, but perhaps you can just get to a form where you have n pivots, where you know you have that upper triangular shape. Remember what pivot positions look like? All right, I thought I had a piece of paper handy, and I did not. Don't want to use my cover sheet here because I want to keep reviewing these one at a time. So A has n pivot positions. Okay, so perhaps I have my matrix. You know, let's make it super arbitrary here. Okay, and I'm able to row reduce that matrix to be upper triangular. You know, I don't know exactly what else I have here. Maybe these are ugly decimals. Okay, you know, certainly with A, B, C, D, they're going to have a lot of unknowns involved and so forth. But I'm able to figure out that these are my pivots. Okay, rather than having to keep going to see, okay, can I get to the identity up here? I know these are the pivots, so I know I have all of these properties together. Okay, so if you can locate the pivots, then you are good to go. Okay, and remember that these are either all true or all false. Okay, so they're all together, true or false. So what that means is if you can show that it doesn't have n pivots, say it has less than n, then you've shown that it's not invertible, that it's not row equivalent to the n by n identity matrix. Okay. D, the equation AX equals 0 has only the trivial solution. Only the trivial solution. So think about what it means to have only the trivial solution. It means it has no free variables. If it has no free variables, then it means that my augmented setup here, right, that we would do for AX equals 0, think about what that augmented setup looks like. I would have my matrix A augmented with zeros, and I'm going to get only the trivial solution. Well, it's still going to be zeros on the augmented side, but that means I'm going to get the identity over here. Or let me not call it I3. Let me not say it's 3 by 3. It's just IN. Okay, so only the trivial solution means that you are invertible, means you're row equivalent, have n pivot positions, get all of that together. Now, just so you're aware, when you start looking at some true-false questions, you know, things that the book or possibly me on a quiz or a test to try to trip you up with, or on the checks for understanding, only is a key word here. If I just say the equation has the trivial solution, every equation has the trivial solution. Every matrix equation, I should say, has the trivial solution. So having the trivial solution is not information really about anything. Okay, it's a nothing statement. Doesn't give you any additional information. It's the only that is really the linchpin there of that theorem. Okay, statement 5 or statement E, the columns of A form a linearly independent set. Okay, again, we know that if I can row reduce to the identity matrix, if I can find n pivots, if I can set up only the trivial solution, that gets me linear independence. Okay, so again, we're just putting these things that we learned in the previous sections together in one theorem. So linear independence is only the trivial solution. It also means it's row equivalent to the identity. It means that it's an invertible matrix. Okay, and any one of these ideas may be easier to produce. Say you have a 2x2 system. You have a 2x2, just a nice simple 2x2 setup. A, B, C, D. Well, if I know that AC does not equal some multiple, let's call it X, of BD, with two vectors, I know that if they're not multiples, they're not linear. They are linearly independent. There is no dependence relationship. Okay. So with two vectors, it's really easy to show linear independence. If you can show linear independence, you get invertibility. You get identity equivalence. You get all of that for free if you can just show one of them. Okay. The linear transformation is 1-to-1. So remember, to be 1-to-1, that meant there was a pivot in every column. If there's a pivot in every column, you have no free variables. Okay, remember pivots corresponded to your basic variables. Think about reduced row echelon form. That means you have that nice setup on the diagonal. At the very least, you have one in every column. And if you have one in every column, you have no free variables. If you have no free variables, then AX equals 0 has only the trivial solution. So it has to be 1-to-1 because there's only one vector that goes to the 0 vector. 0 goes to the 0 vector. There's not any others that I can put into this transformation. Remember, this transformation is T of X equals AX. So that transformation has to be 1-to-1. Okay? The equation AX equals B has at least one solution for each B in Rn. So it's each B. It's all of the vectors. Okay? So if you have a solution for all of the vectors, that means the same thing as the transformation being onto. Okay, the transformation is onto because it covers all of the vectors in B. Okay? And again, that's going to give us the same result. We have in pivots, we have only the trivial solution. B would be one such vector, the 0 vector would be one such B. I can always get it to line up. I cover all of the space. It's all covered by the span. Again, much of this is repetitive because what we're saying is sometimes one of these statements is much easier to prove than another. And so if you get one, you get all of them for free. Okay? If you're onto, you span all of Rn. Okay? So if I have independent vectors, I have span, I get that it's invertible. I get that it's in pivots. I get all of these things together. Okay? This basically means the same thing as onto as well. And then our next one in statement I, or statement 9, the linear transformation is onto. Okay? It takes all of Rn and sends it to Rn. Now remember, it doesn't mean that all the vectors match up perfectly, but it means they are all covered. Okay? Somebody in the domain goes to somebody in the range over here, and the range and the codomain are equal to each other. Okay? Statement 10. Make sure I counted right. Yeah, statement 10, or statement J. There is an n by n matrix C such that CA equals I. And then statement 11 goes right with it. There's an n by n matrix D such that AD equals I, right? This would mean that C is in fact A inverse, or in this one that D is in fact A inverse. Okay, but maybe it's easier to find a matrix, or maybe you're given a matrix that in fact has this relationship. Oh, okay, well, I know these are the case. This must be an inverse then. Maybe I don't know A and D are invertible automatically, but I know their product is the identity. Okay, maybe I don't know that C and A are invertible, but I know their product is the identity. So if you have two matrices that multiply to the identity, that means both of those matrices are invertible. Okay, and then our last one for now, we're actually going to add some things to this as we learn more in later chapters. We're going to add additional statements to our invertible matrix theorem. But statement L, or statement 12, is that the transpose, A transpose, is invertible. Okay, so we know that it can be row reduced to the identity. So that means that if I flip it to the transpose, that's also row reducible to the identity. As if the columns are independent, the rows are independent. Again, we're using that square matrix property there to help us. Okay. Now we don't have a letter for it yet because we haven't learned about generalizing determinants. Okay, we only have a determinant for a 2x2 matrix right now, so we're not able to generalize it just yet. But there's going to be a later statement that we don't have on here yet that says that the determinant of A is not 0. Okay, so if it's invertible, we know the determinant of A is not 0. We're not putting it down there yet because we haven't defined the determinant. We haven't explained how we can generalize the notion of a determinant to a larger matrix, but that is going to be one of our properties. So we're not giving it a letter just yet, but for a 2x2, we can absolutely use that at our disposal, because many times computing the determinant is going to be the easiest thing. You're just multiplying two pairs of numbers and subtracting the results. That's a fairly easy operation for us, so we can do that without too much consternation. Okay. Now, a couple more observations here. Notice that that upper triangular format is very, very useful. Okay. So if you have an upper triangular matrix, so let's remember what upper triangular is. If I have an upper triangular matrix, then that means that down here I have all zeros, where all my numbers are up here. Okay. Up and to the right. So the main diagonal can have numbers. I don't know how far my main diagonal goes. It goes down there. And everything up here can be a number, but everything below that diagonal is a 0. Now, knowing what we know about matrices and pivots, this means that all of these diagonal entries correspond to a pivot position. So if you have an upper triangular matrix, you're good to go. Upper triangular matrix has n pivots. Again, these are square. We're talking about square matrices here, right? We are not talking about non-square matrices in this section. Because if you don't have a square matrix, you can't have an inverse. Because there's no way I can multiply something and get the identity out without that thing having to have different dimensions, and I won't be able to switch it around. Okay, there's no guarantees that you could multiply something and get the identity matrix unless they are both square. Okay. So if you have an upper triangular square matrix, you have n pivots. If you have n pivots, you get the whole thing, right? That gets you the whole thing. So upper triangular is really a nice format that helps us, okay? Now, I'm going to look at a couple of practice problems here that I've got copied. So I have 2, 2, 2, 3, 3, 3. Determine if that matrix is invertible. Sorry, let me get my note page out of the way there for the cover sheet. We're going to determine if that matrix is invertible. Okay, I'm going to write that matrix down here separately. I've got a first column is 2, 2, 2, 3, 3, 3, 4, 4, 4. Now this is a pretty easy matrix to make some identifications about. First, let's label these columns just so I can talk about them: A1, A2, and A3. Easiest thing to notice is that 2 copies of A1, 2 times A1 will get us A3. So this is a dependence relationship, right? 2A1 plus 0A2 minus A3 will get us the 0 vector. Those are A's, not 9's. Get us the 0 vector. So this is a dependence relationship. That means the columns are dependent, linearly dependent. Again, we drop that word linearly a lot because it's linear algebra, so we kind of know it. Check back with your invertible matrix theorem. Okay, well, linear independent is a statement here. So if it's dependent, it's false. That means the whole thing is false. Okay, so the columns are dependent, which means that the invertible matrix theorem tells us that A is not invertible. Okay, sometimes called a singular matrix for not invertible. I don't use that terminology a lot, but you will see that terminology, so at least when I mention it to you. I just usually say not invertible. Okay, not invertible. Okay, let's look at practice problem 2 here. So if I have a certain n by n matrix A, if statement G is not true, so it says statement G of the invertible matrix theorem is not true, so let's go back to G. The equation AX equals B has at least one solution for B in Rn. What can you say about equations of the form AX equals B? Okay, some of those equations may be inconsistent. Not all, right? Remember, we're going to have free variables. If statement G is the case, it's false, then everything else is false, right? AX equals 0 has a non-trivial solution. So if it has a non-trivial solution, then there is going to be a free variable. There's going to be some number of vectors, some number of planes that are not covered by the columns of A. So the columns of A are dependent. If the columns of A are dependent, they don't span all of Rn. So AX equals B is only true for a certain number of vectors B. So you need a specific vector B in order to have, or a vector from a specific set, I should say, in order to have that be a true equation, okay? And then practice problem 3 here. So you have A, B are n by n matrices, and the equation AB times X has a non-trivial solution. So if I have a non-trivial solution, AB, so go back up here, statement D, AX equals 0 has only the trivial solution, okay? So this statement here, ABX has a non-trivial solution, means that D is false, okay? And if D is false, everything is false. And so if D is false, then the matrix AB is not invertible, okay? Because statement A said that the matrix was invertible. Again, it says A is invertible, but the matrix I'm looking at here is actually the product of two matrices, A and B, okay? We also know that the product, if the product is invertible, then the individual components are invertible. So if AB is invertible, A is invertible, and B is invertible. But if I know that AB is not invertible, then the components must not be invertible either. So A is not invertible, and B is not invertible. Now, the question didn't ask me about that. It just asked about AB, but I can get all that stuff for free, right? A is not invertible. B is not invertible. And continuing on. A not invertible, B not invertible. I get all those properties for B. The columns of A are dependent. AX equals 0 has a non-trivial solution. BX equals 0 has a non-trivial solution. I get the entire IMT is false. Okay, all those statements are also false. Okay. One more observation here as I got to the end of those practice problems. One more observation to make. If I know that A squared, so I know A is invertible. So what happens to A squared if A is invertible? What happens to A squared if A is invertible? Well, A squared we know is A times A. A is invertible. The product of two invertible matrices is invertible. So the product of invertible matrices is invertible. So if the product of invertible matrices is invertible, then A squared is invertible. Naturally, then, A cubed is invertible. A to the fourth is invertible. We get all the powers that are invertible. So if I know it's invertible, then I get the rest of the invertible matrix theorem. I get the columns are independent. The columns are independent. If it's a transformation matrix, it's onto, it's 1-to-1, etc. Okay. All right, one more example type problem here. So I'm going to have a transformation. Well, my transformation T acts on the vector x1, x2, writing it in horizontal format there. And it produces 8x1 minus 4x2 negative 6x1 plus 6x2. Okay. And then from there, I want to know what happens to T inverse of x1, x2. Okay, what is the behavior of T inverse? That looks like a weird there one. There we go. So I want to know what happens to T inverse. Or does T inverse not exist? Okay, so possibilities. T inverse exists, T inverse doesn't exist. If it does exist, we want to write down what that transformation looks like. Okay, so let's think about T of x. This is x the vector now. Remember, it's going to be equal to AX. Okay, well, what is A here? A, remember that in this format, these are the rows, right? Because I'm going to have a matrix A times a vector x1, x2. So as I'm going across the row and down the column, I'm going to get something times x1, something times x2. So in this case, that's 8 and -4, -6 and 6. Okay, again, writing that across, -6 and 6. Notice the comma to go to this next row. Okay, well, naturally then, I bet T inverse, not I bet, we know T inverse is going to be A inverse of X. Because if I put T inverse together, then I'm going to put the A's in together, and A inverse times A is going to give me the identity matrix times the vector X itself, okay? So in order to find A inverse, I'm going to do 1 over the determinant of A. Okay, and remember you switch A and D, so switch the ones on the main diagonal, and you make the ones on the opposite diagonal negative. And then, of course, that's going to still get multiplied by x1, x2. Okay, so we need the determinant. So the determinant of A, that's going to be 8 times 6. It's 48. Minus -4 times -6 is a -24. So my determinant is 24. I'm sorry, it's a positive 24, but it's subtracted. There we go. Positive 24, but it's subtracted, so my determinant is 24. So then A inverse X, okay, is going to be 1 over 24. Again, switch these positions, so 6, 8. And this is going to be -4 and -6. Leave those where, oh, sorry, +4 and +6. Leave those where they are, but switch the signs. Okay, and then that's going to get multiplied by x1, x2. Okay, so A inverse the matrix then I can write down as 6 over 24, that's 1/4. 6 over 24, that's 1/4. 4 over 24 is 1/6. And 8 over 24 is 1/3. And then I can write what the transformation would be. T inverse of x1, x2. Okay. Remember, we go across the rows here. So it's 1/4 x1 plus 1/6 x2. And then my second row, 1/4 x1 plus 1/3 x2. And I'd have my transformation, okay? Now, it's very important as you are working problems in this section that you don't just click and get through it and get your score, okay? Make sure you're reading carefully. That'll really help you on those checks for understanding, okay? Just glancing at a couple here real quickly. Let me share that homework view. You look at the homework for this section. Okay, so it shows determine if the matrix is invertible, use as few calculations as possible. Now these are just there's just 4 multiple choice answers. So relatively speaking, you can probably guess the answer. It'll actually give you 2 chances, and if you still get it wrong, it'll give you a similar problem. You can probably get to the answer. So, but if you will help you tremendously, if you will read carefully, think through, and really make sure that you are following, okay, what did I do? Look at this matrix. Oh, the second column is multiple. No, it's not a multiple. Let's check the determinant maybe. So that's -12 on the main diagonal minus a -18 on the off diagonal adds up to 6. 6 isn't 0. Okay, so that I can figure out if the matrix is invertible just from that. Okay, and I can keep applying those down the line. 2, 3, 4. You know, use your things. Make sure you read them carefully. If you do get a question wrong, read why that was the answer. Make sure you think through it. Make some notes for yourself. That will really help you on the checks for understanding and true-false questions that might appear on the test. Okay. All right. So just take all that to your mind. Like look through those properties of the invertible matrix theorem. Again, it's all those things we already know. We're just using them in concert together. Okay. So thank you for joining me here on 2.3. Okay. 2.4 is actually a section we skip. It's called partition matrices. 2.5 is about matrix factorizations, okay? So we have factors of numbers, so we have factors of matrices. We split them up just like we have inverses of numbers and inverses of matrices. Okay, so we look at 2.5 as our next section, and after that we actually go to 2.8 and 2.9. So we do a little bit of skipping around in chapter 2, so you can use that in your preparation. All right, so I'll see you for 2.5 in the next video. And please be in touch if I can be of assistance in your studies.